Hello guys, welcome to Physics Grand. In this video, we are going to investigate what is the dependence of our action variable on the generalized coordinates and time. Okay, so how it varies with generalized coordinates and time. This is what we are going to investigate in this video. So till now, we have already seen that our action, which we denote by S, is nothing but the integral from some time t1 to t2 of our Lagrangian with respect to time. Okay, and how did we integrate it, and what did we do when we studied our principle of least action? We did the following. Okay, so let me write that down. So previously we considered the integral of L over all possible different paths from initial place and time which I'm going to denote it as q of 1 and t, to final place and time, which I'm going to denote it by q of 2 and t2, so t1 and t2. Okay, and we had found that the path corresponding to minimum value of S, where S is given by this relation, is the actual path taken by the system in accordance with equations of motion. And this is what is called as the principle of least action. So in all of these, what we have already done, we are simply considering S as an integral of the Lagrangian. We do not see how it exactly depends on our generalized coordinates and time. Okay, in this video we are going to investigate that particular aspect and see how it depends on these quantities. So for this, let us understand that in our principle of least action, what we did was, if this was our q and t, if this is t1, this is t2, we went from some particular q of 1 comma t1 to some particular q of 2 comma t2, and let us say that this is the actual path that the particle is going to follow. Okay, then what we did in principle of least action was that we found the integral for various different paths with the same initial and starting points. Okay, now the condition that the initial and final positions are the same was written as del q of 1, that is variation of the position at the initial place, is 0, and del q of 2 is 0. This is what we assumed. Okay, and with this we calculated the variation in S, which, if you refer back to our principle of least action video, we will get it as dou L by dou q dot in variation of q substituted over t1 to t2. This we got after integration by parts of the integral over the Lagrangian, plus integral t1 to t2 dou L by dou q minus d by dt of dou L by dou q dot times del q dt. Okay, This was our expression for variation of S, where this variation is basically the variation in these different paths. Okay. So in this, for example, if you consider these two paths, if I consider this path and let's say this path, then the variation is basically taking the difference across these two paths. Okay, the difference in all the coordinates and velocities that corresponds to, so the difference in those two paths correspond to this variation in S. Now what we are going to do is the following. Okay, so before that, let me just write this down. This becomes equal to dou L by dou Q dot at t equal to t2 times del Q of 2 minus dou L by dou Q dot at t equal to t1 del Q of 1 plus integral t1 to t2 dou L by dou Q minus d by dt dou L by dou Q dot del Q dt. Okay, this is the expression for our del S. And when we considered principle of least action, we had assumed that the initial and final positions are fixed. So this variation in the quantities at the initial and final points would go to 0. And for minimizing our action, the condition is that del S must be equal to 0, from where we said that this particular quantity should be equal to 0, and that's how we got our Euler-Lagrange equations. Okay. Now what we are going to do is, we are going to do this. So we have our Q space and time and T1, T2, and I am going to keep our initial position fixed. So Q of 1, T1 is fixed, but I am going to change our, or allow our final position to change. So this is Q2, A, T2, and some other Q2, B, T2. Okay. Now corresponding to these endpoints, these two endpoints, we will have two paths which are physically correct. So let those paths be the following. This is one path, and let's say this is the other path. So this I'm going to call path A, this I'm going to call path B. Okay. So what are the, so these paths are the paths corresponding to which the action is minimum, provided the initial and final positions are given by the respective Q2 of B, Q2 of A for the paths B and A. Okay. So now consider the case where del Q of 1 is equal to 0, but del Q of 2 is not equal to 0, that which is what we have done here. So this difference is del Q of 2. Okay. So in this case, what happens to variation in S? Okay. Now here by variation in S, we take the difference between path A and path B. So that is SB minus SA. This is the variation in S, and to call it variation, the difference must be very close to 0. Okay, so this should tend to 0, but not exactly 0. Only then we can denote it as del S. Okay. Alright. So let us see what happens. So first of all, what are these paths B and A? Let me clarify that. So the path B, okay, is got. So path B is got by minimizing our action with initial and final states Q1 and Q2. Okay, Q2 of B. So if I give our Q and T and two states where this is Q1 and this is q2 of b. Then the path which corresponds to the minimum s will be the correct path, and that path is our path b. Similarly, we can have path A is got by minimizing s with initial and final states. The initial state is still going to remain the same because I'm going to keep the initial state fixed, but our final states is different. Okay. Now we want to find, and again remember, this path A corresponds to that path where the s is minimum for the initial and final positions given by these two things. Okay. What we want to find? We want to find how s, which is corresponding to the correct paths. So we want to find how s corresponding to the correct paths changes when we change the endpoint. Okay. What we mean by this is that clearly the value of s for this path is different than the value of s for this path. And what did this value depend on? This value depends on what is our final positions, and that is what we want to find. We want to find how this s varies for by varying the endpoints. Okay, so that is what we are interested to find. So for this, let us again look at our expression for variation in s. This was given by dou L by dou Q dot at t equal to t2 times del Q of 2 minus dou L by dou Q dot at t equal to t1 into del Q of 1 plus integral t1 to t2 dou L by dou Q minus d by dt dou L by dou Q dot del Q dt. Correct? Now, since both path A and path B correspond to the paths with minimum s, okay, corresponding to the path with minimum s, our Euler-Lagrange equations must still be satisfied for those two paths. Okay, which means our this term is still going to be equal to 0 because s is minimum for both paths. This can only happen if this term is 0. Okay. Also, we have already said that our initial position is fixed, so the variation in the initial position is going to be 0. The initial position doesn't change, whereas our variation in the final position is given by q of 2b minus q of 2a, because here there is a finite variation in our final position, whereas there is no variation in our initial position. So this implies that del s is equal to dou L by dou Q dot at t equal to t2 times del Q of 2. Okay, but we know that this is equal to our generalized momentum, and at t equal to t2 we will get p2. Okay, so finally we have del s is equal to p2. I should write it like this. So let me be consistent with the notation. So this is p2, this is p2 times del q of 2. So from this we get that dou s by dou q of 2 is equal to p of 2. Okay, so remember, this relation is valid only for values of q, del q and p at the endpoints. Okay, not for any values. Okay. Now for many coordinates, this is only for one q. Similarly, for many coordinates, the analysis is exactly the same, and we will get for many coordinates we have del s equal to summation over I pi of 2 del qi of 2, which implies dou s by dou qi of 2 is equal to pi of 2. Okay, but I can choose our position 2 to be anything. What I mean by that is that in our curve here, where did that go? Yeah. So here I could have chosen the final point to be over here, corresponding to some other time. Okay. Or if you consider this same time, I can consider paths for any final position, and corresponding to that I can find the variation in S. Okay, which means our Q2 is not actually a constant, it's a variable which can vary through all possible values of Q's. Okay, so to make sure that, or to express that in the equation, we are just going to drop this particular superscript. Okay, and the justification for that is that the value for this pi and qi at the endpoints can take any value. I can choose a particular value, any value, and corresponding to that I can find a particular path which minimizes our action, and from there I can find a variation in the action by varying our endpoints slightly, and such a variation is expressed in this manner. And this particular statement, because of this statement, we can just use the notation this as del qi and pi of 2 as just pi. Okay, so but we have to always keep in mind the following thing: this variation in endpoints, which is this guy. So this variation in endpoints and value of momenta at t equal to t2 is what is represented by del qi and pi. So what I mean is that this del qi and pi do not correspond to the values at any time, but they correspond to the values at the endpoints, which is t equal to t2. Okay, so this notation makes it more clear, but this notation makes the equation look better. Okay, that's the only difference, because this it is just notation. This just says explicitly that the value for the endpoints coordinates and momenta can be any value that we want, and corresponding to that we'll have a particular S, and what we are finding the relation is the variation of that S with respect to these quantities. So finally what we have established is that the variation, or dou S by dou Qi is equal to Pi, where our Qi and Pi correspond to the values at the endpoints, not any value in between. Okay. Alright, thank you for watching. In the next video we will see how our action depends on the ending time. Okay, that is t2, how it depends on t2. So that will be the topic for our next video. Thank you for watching. See you next time.